Other types of equilibria we can look at besides acids and bases are solubility of salts. And this is just another application of how we use the equilibrium rules and calculations. So to start with solubility, we know that salts, ionic compounds, dissolve in water. They produce ions, and sometimes those ions can collide, they can get close to each other and reform the solid. So eventually we reach an equilibrium. The equilibrium position is when the rate of dissolving is equal to the rate of recrystallization. And that's equilibrium for that. Okay, so calcium fluoride, for example, will split into calcium ions and fluoride ions. It reaches equilibrium when you have as many calcium fluoride formula units splitting as you have forming. This will occur in a saturated solution. And that means no more solid will dissolve without the solid reforming at equilibrium. Okay, it can't get any more to dissolve than it already is. So really, when we talk about insoluble compounds, we really just mean that they have very low solubilities. There's really nothing that's completely insoluble. The solubility product is nothing more than an equilibrium constant. It's called KSP. It's calculated exactly the same way. Here's our calcium fluoride splitting or ionizing into calcium and fluoride ions. The solubility product is the concentration of calcium 2 plus times the concentration of fluoride ions squared, because it has a coefficient of 2. Notice that CaF2 solid is not listed in our expression because solids don't show up in equilibrium expressions. Okay? Essentially what that means is that once you're at equilibrium, it doesn't matter how much solid you add. It's not going to affect the equilibrium position. You can add a ton more solid, but if you're already at equilibrium, that's the maximum amount that's going to dissolve. So it doesn't matter how much you add. It's not going to affect the equilibrium position at all, and therefore it doesn't belong in our expression. These are KSP values from your text of all sorts of different salts, and you can see if you think about their KSP values, the smaller the KSP value gets, the smaller the concentration of ions must be, and therefore the less soluble things are. So you can judge sometimes relative solubilities or approximate solubilities by looking at how big KSP is. Okay, copper 1 bromide has a solubility of 2.0 times 10 to the minus 4 moles per liter. That means the maximum amount of copper 1 bromide that will dissolve is 2.0 times 10 to the minus 4 moles per liter at 25 C. We want to find the KSP value for CuBr. So we can calculate KSP simply the same way you'd calculate K. Okay? Solubility is the maximum amount of solute that dissolves in a liter of water. So since CuBr is a binary salt, meaning it's made of 1 copper ion and 1 bromide ion per formula unit, this is actually pretty easy. Okay? So CuBr is in equilibrium with Cu plus and Br minus. We don't care about the solids concentration initially. What we care about is what happens over the course of the dissolving. Now, we know that the maximum amount of the salt that's going to dissolve is 2.0 times 10 to the minus 4. It doesn't matter how much we start with, but only 2.0 times 10 to the minus 4 moles per liter are going to dissolve. So that's our change. It's negative on the solid side because that's being taken away, and it's positive for the Cu plus and the Br minus. It doesn't matter what the solid's concentration is or how much solid I have at equilibrium, but it does matter how much of the Cu plus and Br minus I have. I have 2.0 times 10 to the minus 4th of each of those because it's 1 mole to 1 mole to 1 mole. So our KSP value then is just going to be the product of those two, or 2.0 times 10 to the minus 4th squared, 4.0 times 10 to the minus 8. That's our KSP value. So for copper iodate, we have a KSP value, 1.4 times 10 to the minus 7th, and we want to know its solubility. In other words, what's the maximum amount, moles per liter, of copper iodate that will dissolve. The solubility is going to be X in your ice chart. So you set up your ice chart, okay? Copper iodate dissolves into copper plus 2 and 2 iodate ions, 2 moles of iodate, okay? Now that is going to affect the way you set up your ice chart. Now I don't care what our initial concentration of CuIO3 is, but there is initially no Cu2 plus and no IO3 minus. Some of the CuIO3 will go down by X. The same amount will go up by X for copper 2, but since it's 2 moles of IO3 minus per mole of copper iodate, 2X is the amount that will increase. And then at equilibrium, that means that our concentration of Cu plus 2 is X, and our concentration of IO3 minus is 2X. Plug that into your KSP expression, Cu2 plus times IO3 squared. X times 2x squared, or 4x cubed, is equal to 1.4 times 10 to the minus 7. That's our KSP value. So divide by 4 and take the cube root. You get 3.3 times 10 to the minus 3rd moles per liter. That's the concentration. That's the solubility of this salt at 25C. It's very low solubility. Not very much is going to dissolve. So we would say copper 1 iodate or copper 2 iodate is an insoluble salt if we were doing it qualitatively. But some of it dissolves, just not very much. You can compare solubilities between salts using your KSP values, but only if those compounds that you're comparing split into the same number of ions. Okay, so calcium sulfate, copper 2 carbonate, and silver iodide, when they split, they each split into 2 ions apiece. So because they produce the same number of ions in solution, we can look at their KSP values, and we can say, well, the one with the largest KSP value, in this case it's calcium sulfate, is the most soluble. And the one with the smallest KSP value would be copper 2 carbonate, and that would have the lowest solubility. Okay, so why that works? It works because if you have the same number of ions, then you're calculating the molar, for in this case we have 2 ions apiece, calculating the molar solubility is just the square root of KSP. So the one with the larger KSP value is going to also have the largest square root value, and that means it's the largest solubility. If your salts split into different numbers of ions, you can't use your KSP value to determine which is the most soluble. You actually have to calculate the solubility for each one and compare them, okay? Because your KSP expression is going to be different. It's going to have exponents in there, okay? So here's an example. We've got copper sulfide, copper 2 sulfide, CuS, that splits into 2 ions. Silver sulfide, Ag2S, splits into 3 ions, and bismuth sulfide, Bi2S3, splits into 5 ions. Look at their KSPs. If you just looked at the middle column, the one with the smallest KSP, Bi2S3, should be the least soluble if we were just comparing KSPs. But if you calculate the molar solubility, the X value for each of these salts, you see that actually Bi2S3 has the greatest solubility. It's the most soluble of all 3 of those salts. So you can't compare solubilities of salts that have different numbers of ions by looking at just KSP. You have to calculate X. So as far as the common ion effect goes with solubilities, it's the same thing. Okay? If you try to dissolve a solid into a solution that already contains one of the ions in that solid, less will dissolve. Common ion effect, remember, shifts it back towards the left. And in this case, in the case of solubility, the left is where the solid is. So if you shift the equilibrium of a dissolving of a solubility back to the left, you're making less dissolve. Here's an example. We're going to try to dissolve CaF2. We're going to find its solubility if KSP is 4.0 times 10 to the minus 11. And we're going to put this in a solution that already contains some fluoride ions. Okay? So it's an equilibrium problem, a common ion problem. All right? That means we need an ice table. CaF2, not important. Calcium ion concentration at the beginning is 0, but we already have 0.025 moles per liter of fluoride. The amount of CaF2 is going to go down by X. The amount of Ca2 plus is going to go up by X. The amount of F minus is going to go up by 2X because it has a coefficient of 2. So at equilibrium, my Ca2 plus concentration is represented by X, and my F minus concentration is represented by 0.025 plus 2X. Plugging that into the KSP expression, concentration calcium times concentration fluoride squared, X times the square of 2X plus 0.025. Just solve for X. Okay, solving for X, we can make the approximation to get rid of the quadratic there, and so 2X plus 0.025 is essentially just going to be 0.025 squared. X times that, solve for X, you get 6.4 times 10 to the minus 8. X is the concentration of calcium ions that is going to form in solution as this stuff dissolves. X is the solubility of this salt. So a solubility of this particular salt is very, very small if we already have fluoride ions in solution. Now, if you change the pH of a solution, you're changing the hydrogen ion concentration or hydroxide ion concentration. That can affect solubility if it creates a common ion effect. Okay, so magnesium hydroxide is a solid. It'll dissolve into magnesium and hydroxide ions. But if you try to do this in a high pH situation, high pH means basic. Basic means lots more OH minus. That's a common ion effect. What's going to happen if you try to dissolve magnesium hydroxide in a basic solution? Less is going to dissolve. Okay. What about silver phosphate? That splits into 3 silver ions and 1 phosphate ion. What if you add H+? What is the H+ going to do to this situation if I add H+? Well, if I add H+, it's going to combine with the phosphate ion to make phosphoric acid, which is a weak acid, which means it prefers to be the molecule H3PO4. So if you use up the phosphate, that's going to remove phosphate from your equilibrium expression, and it's going to cause the equilibrium to shift to the right. And that means more of your silver phosphate will dissolve. It'll increase the solubility. So solubility equilibria is just another type of equilibrium. It's actually a little bit easy because you don't have a denominator in your equilibrium expression. It's just the numerators. So it makes the calculations a little bit easier and a little bit easier to work with.